So we've been talking a lot about the origin of the universe, and we got a chance to watch a video last time about the nature and origin of the universe. What I'd like to talk about today is the structure and the fate of the universe and how we determine the bulk properties of the universe. The first place I want to start is with Hubble's law. Hubble is, as you recall, was the gentleman who observed that all galaxies are moving away from us, and the further away they are, the faster they're moving away from us. And this was explained by the expansion of the universe. And the expansion of the universe is something that is ongoing. It's happening even today, and it is telling us not only what happened in the past, but it also tells us what's going to happen in the future. So to remind you from your balloon activity, we had this example of a stretching balloon surface, and that stretching balloon surface is going to effectively give us more space all the time. So the universe is not expanding into something. The entire universe itself always gets bigger, and this expansion is something that we can measure through the positions and velocities of the galaxies. So let's talk about the cosmological principle, because we have to have some underpinning of our ideas of the nature of the universe before we can start studying it. We have to decide how we're going to look at the universe and see, then we can go out and look and see if what we've decided is correct or not. So our principle here, the cosmological principle, is that the universe should look the same no matter where you are within it. And this is built upon the fact that when we look in every direction in the universe, we see about the same stuff. It can't be proven because we've never been everywhere in the universe, but considering what we have seen, we suspect that it is true because we haven't seen anything that would tell us any differently. The other reason is that if it isn't true, it means we're at the center of the universe, and that has never been shown to be correct, because the Earth isn't at the center of the universe, our sun is not at the center of the galaxy is not at the center of our cluster of galaxies, and so forth. So we take as a principle, as a basic premise, that the universe looks about the same no matter where you are in it. So what does that mean? That means that matter is evenly distributed on large scales, so that's called homogeneous, right? There's no center or edge, at least that we know of. So we've never seen an edge, and we're not at the center. And it's, again, this is consistent with all observations. The other thing we have to remember about the universe is that in addition to being homogeneous, in other words, evenly distributed everywhere, it's also isotropic, which means it's the same in every direction. Okay, so homogeneous means the same stuff is everywhere. Isotropic means it's the same in every single direction. Now, if that's the case, we can look at the expansion of the universe and try to make some predictions about what has happened in the past and what's going to happen in the future. And all of this hinges on the amount of matter in the universe. And if you recall, let me just write this down real quick. If you recall, we have these categories of material. We have matter, which is you and me. That was about 4% of the universe that we think, based on observations. We have dark matter, and then we have dark energy. And the question is, what is the distribution, or what is the fraction of the universe that is dark matter, dark energy, and regular matter? And the different fractions are going to give us different situations. For example, if there's a lot of dark matter and a lot of dark energy in the universe, if there isn't enough dark matter in the universe is going to continue to expand forever, right? So you imagine here's the origin of the universe of the Big Bang down here, right? The universe is expanding, so here's a little piece of the universe getting bigger and bigger and bigger, and the expansion is driven by dark energy. The contraction of the universe is driven by dark matter. If we don't have enough dark matter to haul back the expansion of the universe, it's just going to coast and have a uniform expansion forever. In other words, it'll just get bigger and bigger and bigger and bigger. Now, contrast that with this first one over here, which is if we have a lot of dark matter, then we can recollapse the universe. So what that means is that you've got this dark energy, which is pushing the universe apart, but eventually the dark matter starts to win over, and you can recollapse back to another Big Bang. I didn't put this one out in detail because this one has been ruled out. Okay, this one has been ruled out as a possibility. And in fact, based on observations, the critical universe, which shows that we coast to a fixed size, right? So eventually you get to the point where the size stays the same. That one's been ruled out too. So we have the coasting universe, this guy right here, which says we just expand at a uniform rate. The other alternative is if there's even more dark energy, you can expand it at an ever-accelerating rate. So that means that the universe is expanding, so the expansion of the universe is getting faster, which means you're on an exponential expansion rate. So the rate increases as you go bigger and bigger and bigger, and eventually you get to the point where the expansion rate is so fast that it rips apart the fabric of space-time itself. Now that's going to happen a really long time in the future from now, but that's the idea, that we accelerate forever and ever and ever. So these are the two things we're trying to gather data to see if we're coasting or accelerating. And I'll give you the punchline. The punchline is the newest data out says we're accelerating, that eventually the universe will reach an expansion rate that's so vast it'll just rip itself apart some hundreds of billions of years from now. Okay, once we've decided what model we're looking at, that's going to determine the age of the universe depending on how much dark matter and dark energy there is. And the reason for that is that imagine we look at these two cases here. So this is us, this is the present, right? And we know that the universe has, or at least the region of the universe we're interested in, has a particular size. And that is whatever the size is today. If you're in a coasting universe, then you get smaller faster than you do in an accelerating universe, which means that pushes the origin, the date of the origin of the universe back in time. So if we can measure the age of the universe, we can figure out this discrepancy here and figure out if we're in the accelerating universe or the coasting universe. Now, how are we going to do this? We need to look for some kind of distance indicator that we can find very, very far away. And we've talked about these things before. These are supernova explosions. They outshine entire galaxies. This happens when you have a white dwarf that's being orbited by a larger star. That larger star dumps mass onto the white dwarf. The white dwarf eventually reaches its limit of mass where it collapses into a neutron star and it explodes in a giant supernova explosion, and you wind up with something that outshines the entire galaxy. The cool thing about these type 1a supernovas, these white dwarf supernovas, is that they always have the same peak brightness. So if we can find one right here next to a galaxy, they all have the same peak brightness, which means that you can look at these things and tell the relative distances of the galaxies. So I can just look at this and I can say, well, if all of these things have the same peak brightness, then the dimmest one's going to be furthest away. So this one is the farthest away. So this is the farthest one away because it's the dimmest. This one's the middle distance away because it's about the middle brightness, and this one's the closest. And if you're very careful about your observations, you can use this coupled with the very careful measurements of the brightness of it, the apparent brightness, to get an actual distance away. And that is something we can use to determine the expansion, because we can measure the velocity with spectroscopy and Doppler shift. We measure the distance to the galaxy very precisely using the supernova, and that gives us a Hubble law that reaches very, very far out into the universe. And that's important because we need to see far back in time in order to figure out which path we're on. If we're on the accelerating universe, this path right here, or the coasting universe, this path right here. Okay, so let's see what the data tells us. This is the supernova data that's been taken over the last decade or so, and what we're looking at here is the average distance between the galaxies. This is based on redshift, right? So this is how far away the galaxies are from us. And this is the time, in other words, the time it takes light to travel to us, right? So if you think about how far in the past, this is the look back time, and this is based on the apparent brightness, right? So what this graph is really saying is that based on the redshift, how far away do we expect the galaxy to be compared to its brightness, how far away it really is. And if those two numbers are the same, everything should rely on this line right here, this coasting line, because that means that the distance we estimate from the redshift should equal the look-back time distance that we get from the supernova. If they're the same, we should get a straight line. That means we're coasting. If they're above the line, it means that they're further away than we thought they were. And if they're below the line, it means they're closer than we thought they were. And that can distinguish between the critical universe or the accelerating universe. universe. And so if you look at these data, you know, back in the early 90s and mid 90s, these were the supernova data taking us out to here. And right around here was when I was in graduate school. And those data couldn't really distinguish between the observations of the critical coasting or accelerating universe. We had pretty much ruled out the recollapsing universe at that point because the data was so far above the recollapsing line, but we hadn't been able to rule out these other three. So a student who was, a recent graduate who was a postdoc at the University of Washington at the time was looking into these observations and taking more data. His name was Adam Rees, and he basically took a lot of these other data and determined that all this stuff lies on the accelerating universe. And here we are today where we have a clear indication that the galaxies are farther away than we think they are. Right? In other words, the universe is older, slightly older than we thought it was. He's since won the Nobel Prize for this, which is pretty cool. And it was neat to be working with him when he did that, to see him taking the observations that ultimately proved that the universe was accelerating instead of coasting. So this tells us that the universe is accelerating at a ever-increasing rate. And you can see now, this is again looking back into the past, but because we know what's happening in the past over here, we can tell what's going to happen in the future. And so in the future, our universe is going to accelerate more and more and more and more and more until eventually, sometime much, much later, it will rip apart the universe, space-time itself. And this is, if you look at the units here, right, this is 10 billion years from now. So 10 billion years from now, it's not that much different. So that's the age the universe is pretty much already. So we're talking hundreds of billions, if not hundreds of billions of years where this is going to be a problem. So we can just keep not worrying about that for the time being. But it does tell us something very important about the fundamental nature of the universe. Okay. Now, if you can know what happens with the expansion rate into the future, you can tell what happens from the expansion rate into the past, because we just run the clock backwards. And I want to take a minute to put some details into the video you watched last time about the origin of the universe. Where did we all come from? One of the basic tenets of physics is that if you take something, and so this is the second since the Big Bang. This is us today. If you take something and compress it, so this universe expanded, so if we turn back the clock, it's being compressed, the temperature increases, right? So as we compress, go back in time, the temperature increases. So that means there must have been an early hot period of the universe that was about 10 to the 32 or 10 to the 33 degrees Kelvin, which was incredibly hot. Beyond that, after this point, we have no idea what the universe was like because the equations break down, our physics equations break down, are not capable of giving us any sensible answers earlier than that. However, I want to point out that that's at 10 to the minus 44 seconds after the Big Bang. Right? So our physics tells us everything about the universe from 13.7 billion years after the Big Bang, which is today, back to 10 to the minus 34 or 44 seconds after the Big Bang, which is practically instantaneous. That would be like if I were to give a grade for how well physicists understood the universe, they would have a 99.9999944 on this exam because they understand everything about the universe up to 10 to the minus 44 seconds after the Big Bang, which is a pretty good score. I'd probably round it up to 100. But we're still mad because we don't know exactly what happened back there. And it's possible we may never know what happened right before that point. But we've got a pretty good job of what happened all the way up until that point. Back in the early universe, there was really no distinguishing feature between matter and energy. We know from Einstein that energy and mass are equivalent. They can convert back and forth to each other. And effectively, this was happening spontaneously throughout the universe early on, because anytime you would create a particle, such as an electron or a proton, they would annihilate immediately with an antiparticle. An antiparticle is merely the same properties of the particle but has opposite charge, and they would create energy in the form of photons, and then those photons could smack together and create positron-electron pairs, and so on and so forth, just back and forth and back and forth. It was just constant obliteration of particles and antiparticles. However, there happened to be, just statistically, a slight slightly more particles than antiparticles, and so when everything got finished annihilating with each other, we wound up with a universe that had some ordinary matter left over in it. Okay, so this is a picture that they've got a diagram similar to this in your book. You can go through the details of all these different steps. I just want to point out some of the key ones and talk about sort of where things come from as a form of, as a function of time in the universe. So let's first look at something called the Plunk Era. And the Plunk Era, this was, again, 10 to the minus 43 seconds after the Big Bang. This is the area where we don't know what's really happening. Okay, so I put a big question mark here because there's the problem we have is that the two theories of the universe that work really well, quantum mechanics and gravity, do not play together at this scale. And the reason for that is because quantum mechanics is the study of the very small, gravity is the study of the very big, and when you crush the universe back into such a small area, you now have the very, very massive, the very, very big, occupying a very small space, and the theories just break down. So this is the area where we're expecting the next Nobel Prize, because we don't know what's happening with quantum gravity. But whatever is happening back here, it has to be dominated by quantum effects on large masses. And we just, at this point in physics, just have to put a big question mark there. Now, what do we think is happening back there? Because of course people are working on this, and this is something that we're very interested in trying to find out what happens back here. Well, if we look at the history of the universe, we can put the temperature on the x-axis here, which again, this is effectively representing time going backwards. So this is time as well as temperature, because as I go back in time, it gets hotter and hotter and hotter. Well, we know from experiment that at low temperatures, the four forces of nature, that we have the strong force, which governs the nucleus of the atom. We have the electromagnetic force, which governs chemistry. It governs how atoms interact. We have the weak force, which governs radioactive decay. And then we have gravity, which is the force we're most familiar with, which is what sticks us to the planet. All those have been very, very well studied at low temperatures. We do this in the laboratory. And all of them are distinct. They cannot be combined. They're all very, very different forces, and they work on different scales with different properties. However, in our particle accelerators, we can do experiments at higher and higher temperature, and we have discovered that if you go to a high enough temperature, the electromagnetic and weak force combine and become indistinguishable, effectively becoming the same force, which we call the electroweak force. Go back higher temperatures, again, in laboratory experiments, we find that the strong force and the electroweak force become indistinguishable. And this is called the GUT force. GUT stands for Grand Unified Theory. And this is really where our theory of quantum mechanics is today. Quantum mechanics tells us how all of this stuff interacts. And this was the hallmark of the last century and into this early century of this, the 21st century. Figuring out how all of these forces worked was something that is a testament to human achievement, because every experiment we've done proves this out. Meanwhile, Einstein has come up with a theory of gravity that has been tested and tested and tested, and is also correct as far as every experiment we've ever known. However, at these high temperatures, these forces are still completely distinct, and we have no way beyond here of testing this in the laboratory. The particle accelerators just aren't powerful enough to create the high enough temperatures that we need to test this. But there is a laboratory. It was called the early universe, and the early universe gets hotter and hotter and hotter, and we suspect that at some temperature earlier than 10 to the minus 43, because theoretically they're distinct all the way up to that, all of these forces combine into one grand unified force that we don't really have a name for. We call it quantum gravity, we call it the super force, we call it the super gut force, right? This is effectively the unification of all four forces in nature. Again, this is beyond where we can observe in the universe, and right now it's theoretically beyond what we can even calculate. So we don't know what it is. And but that's what we suspect, and we suspect that because the unification of the other three forces works so well. Why wouldn't all four forces unify? Now, that doesn't mean it does do that. Just because we like to think it's elegant that it would all unify into one big force doesn't mean nature has to play that game. It could be that gravity is completely different from every other force. And in fact, the best competing idea right now for how this works is that back at these temperatures and energies, we have effectively a gravitational force that is operating over multiple dimensions. And these gravitational force operating over multiple dimensions gives us an idea of why gravity is so weak, and also how it might combine through multiple dimensions, and not 4 dimensions, but something like 11 dimensions. And this is called string theory. And that's a whole course in and of itself. If you want to go watch a cool video about it, Brian Greene has some interesting stuff about it in something called The Elegant Universe, and I suggest you check that out. But string theory hasn't provided any predictive hypotheses about the early origin of the universe. So right now it's just a theoretical idea. But that's what we think is going to happen. Okay, so I guess we have all these, yeah, who knows? String idea, I call it, because theory is usually reserved for things that we've tested. Okay, so once we get out of the Plunk era, we have something called the Gut era, which is the grand unified theory era. This means that gravity and the other 3 forces have separated, and we are now able to think about creating elementary particles, things like electrons, protons, neutrons. However, we have this annihilation of energy and mass going on all the time. Now you'll notice something interesting here, that this is meant to represent the expansion of the universe, and during this period of time we have this rapid expansion that was much, much faster than what we see now today, and this is called inflation. And this is necessary because if we look at the cosmic microwave background, it is essentially a uniform temperature. But for something to be a uniform temperature, it has to be in equilibrium with itself. In other words, it has to be close enough for long enough time so that the temperatures can equalize. And those temperatures can't equalize unless if you're too big, this side of the universe never sees this side of the universe, or if it happens too quickly. And given the speed, we've gone from 10 to the minus 43 to 10 to the minus 38 seconds, which is shorter than any instant you can imagine. The universe had to have started very, very small to be in equilibrium, and then suddenly got big enough for it to match the observations as we go forward in time. So this period of inflation is a key element of the Big Bang, and it's something that has just been borne out in the cosmic microwave background. We discussed that a little while ago. In the polarization of the light from the cosmic microwave background has demonstrated that inflation happened. Okay, so the next era is something called the Electroweak Area. So the strong force has broken off from the electromagnetic and weak forces, and this is where we can start to get elementary particles. So every single particle in your body was created at this time. Well, I should be careful about that. There was still annihilation back and forth, but the particles in your body could exist at this point in time. Up to 10 to the minus 10 seconds after the Big Bang. So this is called the Electroweak Era. Then we move into the Particle Era, where we've now annihilated most of the antimatter out of the universe, and we have elementary particles that we know of. And this takes us down to about 0.001 seconds, and we have 1 extra proton for every billion proton-antiproton pairs, which means that about a billionth of the universe gets annihilated into energy, and we're what's left over. So this is a statistical property of the universe which we're pretty happy about, because I'm made of ordinary matter, and if there had been exactly identical amounts of matter and antimatter, no regular matter would be here. After that, we get into the period of nucleosynthesis, and this is where nuclei begin to fuse, and we can get what we would consider real atoms, right? So that would be things like protons, neutrons, and electrons. And they can begin to combine into hydrogen and helium. This is where we get, at about 3 minutes after the Big Bang, we get the crystallizing out of the hydrogen, helium, and lithium. All that is ever going to be created in the universe is created at this point in time. So every hydrogen atom in your body was made at this point in time. Now we keep going forward to the area of nuclei. This is where we start to have the atoms forming into hydrogen and helium in abundance. These atoms are now permeating the universe, but the universe at this point, at 3 minutes after the Big Bang, for the next 380,000 years, can't do much but just kind of bounce around off each other. They're emitting light, light's being absorbed by them, the light can't permeate the universe, and the universe is this opaque sea of hydrogen and helium that we can't really do anything with. Stars can't form, it's way too hot. So this is, we're just kind of waiting for the pot to cool down so something can take place. We have all of the ingredients we need for stars and galaxies, but it hasn't had a chance to cool to the point where we can start to crystallize these things. However, after about 380,000 years, the universe cools enough that it becomes opaque to, or transparent to light, and the cosmic microwave background is released into the universe from here. And this is where we can start to form true atoms, atoms that have electrons around them. So hydrogen can form into molecules, helium can form into helium atoms, with true atoms with electrons around them that can perform chemical reactions. And this is where we start to get star formation. Stars can begin to form here because atoms will begin to draw each other together via gravitational collapse, and the first stars are formed. And this is where we begin to, between 380,000 years and the first billion years, we begin to generate the first generation of carbon and nitrogen and oxygen and the things that make up everything we are. So this is really where all of the atoms in your body, all of the ones that can be formed in star formation, come into play. Then we move into the era of galaxies. These stars and the dark matter that surrounds them start to clump up into galaxies, which creates more regions of star formation. And at about 1 billion years up until now, we are in what's called the era of galaxies. Some people call it the stellariferous age because this is when stars dominate the light of the universe. And that happens for the next 13 billion years until you get to us, which is right here. And we live this right here, while it's still represented the same size, this is the vast majority of the time that the universe has been around. About 13 billion of the 14 billion years have been spent up here. Okay, so that's something like that has to happen, right? The details, the things that we're trying to do as research scientists now is figure out exactly how it happened. What is the distribution of material? What is the percentages of the materials? And so our job now is to go out into space and look for observations that will tell us exactly how this took place. And that's what we can start to do here. Before we do that, I just want to point out that there's, again, 3 types of material in the universe that we're worried about. We have regular matter. We have something called dark matter. And we have something called dark energy. And for the sake of argument, we kind of lump this kind of stuff together sometimes into dark matter and dark energy, or we lump dark matter and matter together, depending on whether we're talking about gravity or we're talking about the expansion. But a parameter that we're going to look at now is something called omega. And omega is just the ratio of the mass of the universe relative to the mass of the critical universe. So remember, critical universe was enough material to basically coast forever, right? So an omega of 1 would be a universe that's that has just enough material to hold it back. So what we're going to look at here is a comparison between dark matter and dark energy. Dark matter is on the x-axis. So this is, we'll call this dark matter. So this is the fraction of dark matter in the universe compared to our critical case. This is dark energy over here. And let's see if we can figure out what will happen if we have more dark energy or more dark matter, right? If we have more dark energy, remember dark energy is the thing pushing the universe apart. So if I have more dark energy, eventually I can have so much dark energy that there's no way for me to turn back the clock and compress it back in time. And so no Big Bang would have ever happened. But we've observed a Big Bang, so we can rule out all of this space up here. This can't exist. We can't have dark matter or dark energy greater than about 1.1 because this right here is, we know we had a Big Bang, so we can rule that out. This is, if we have enough dark matter, you eventually could recollapse the universe. Well, we've already seen that the universe is expanding and it's expanding exponentially, so we know we're not going to recollapse. Okay, so we know that we have to be expanding forever, which represents this whole thing right here. Now, there are three possibilities in the expanding forever. We could be an open universe, which means that we have a open curvature, that the effectively the universe is infinite, and if there's any curvature of the universe, it's kind of a negative curvature like a saddle. We could be a closed universe where effectively we have a finite size, but we're curved back on itself. Or we can have a flat universe, which effectively is just an infinite universe which stretches out in all directions. And the infinite universe that stretches out in all directions, that is perfectly flat, has the feature that the amount of dark matter and dark energy adds up to be equal to 1. Okay, so that's what that line is right there. So now the question is, what sort of observations can we make about this? Well, we can go out and measure the amount of dark matter. We can go out and measure the amount of dark energy. And we'd like to do this with a bunch of different experiments to see what we find. So let's put some experiments on here and see what we see. The first one is looking at globular clusters, right? So this is globular clusters. If you recall, we can look at a globular cluster and we can tell both its age and its distance. Okay, and the age and distance tells us, well, the distance doesn't tell us too much, but the age is important because we can't find anything that is, if we can't find anything that's older than the we can't find anything that's older than the universe itself. So if we find the oldest globular clusters we know of, that's going to fix the amount of dark matter and dark energy in the universe, because it's going to tell us what the age of the universe is. It's effectively an independent age of the universe. The age of the universe is, again, that tells us whether we're, if it happened further back in time than we think, we're in an accelerating universe. If it happened closer than we think, we're in a non-accelerating universe. And so this gives us a range of dark matter, basically how much dark matter is there to hold back this accelerating or expanding universe. And so if you look at the globular clusters, it gives us a range of dark matter between, say, 0.02 and 0.2 and 0.5, right? It doesn't give us any limit on dark energy, because dark energy could be expanding the universe at a lesser rate or a greater rate. So we get this region in here where we know that this is the possibility of dark matter from globular clusters. So this again gives us from 0.2 to 0.5. 50% compared to the critical universe is dark matter, 0.2% or 20% compared to the critical mass of the universe. Okay, but again, that's no constraints over dark energy. So let's go get another one. Let's look at supernova. Supernova, that's the stuff that we worked out with the age of the universe looking back in time. And if they're further away than we think, we know we have to be in an accelerating universe. And if they're closer than we think, we know we have to be on a coasting universe. And you can see that this is the region that it blocks out. And it overlaps with the globular clusters here. So if we're going to take these two observations, we're going to have to say that if both observations are correct, the supernova is limiting us to this, and globular clusters limit us to this, the overlap is the most likely region, which tells us that we have about 70% dark matter and or dark energy and about 25% dark matter. So that gives it, but it's pretty broad, right? I mean, this is a large region here. So we've done other experiments. We've looked at Boomerang, which was a cosmic microwave background experiment. That limited us to a flat universe based on observations of the cosmic microwave background. We've done further experiments with WMAP, which constrain that even further. And what that tells us, let me go back to that. What that tells us is that the region that overlaps all of this stuff is the most likely area in this graph for the likely values of dark matter and dark energy. And if I look at that, I get something like 70% dark energy, and I get something like 25% dark matter, and then the rest of us is us, which is 4 to 5%. Now we've done one other experiment which isn't on here, which is Plunk, and that tells us, I think their values were 68%, and for dark energy, 28% for dark matter, and then the remainder is matter. Right? So a little bit different than what we had before, but again, they just had some more observations which put us right there. So we're starting to look like we live on a flat universe. So the flat universe is infinite, extends forever in space. It has an age of about 13.7 billion years old, and it has about 70% dark energy, 25% dark matter, and about 5% regular matter, as just rough numbers. And that's the universe we live in. Now, the exciting thing about that is all of those explorations tell us pretty much everything about the universe except what happened the instant it began. And of course, that is now the area of research, because we sure would like to know where the universe came from. There's some interesting questions you might have about that if you ask where the universe came from. We don't know anything that existed before the Big Bang. And in fact, if you're very, very particular about it, considering time and space was created during the Big Bang, nothing could exist before the Big Bang. And it's a unique way to think about nothing, that nothing could give you something. But it's entirely possible that the universe was created out of nothing because there was nothing before the Big Bang. That's a very hard thing to wrap your mind around. But it's something physicists are working on trying to explore. Okay. So that's all I have planned today, and next week we're going to start on our discussion of life in the universe. We're going to bring this all back from talking about cosmology and the origin of the universe and try to figure out where is everybody. And if there are no questions, I will see you on Tuesday. All right, have a good weekend.
Kicked from this